So we're going to start pouring kind of right here. And so I'm just going to pour rows and just sort of go back down the table that way. So that's what to expect. So the first one is composition A. And so that was a little bit low on sodium carbonate, which is the flux, which should make it thinner. It's about typical on the calcium carbonate. And then this one had copper and manganese, right? So about a medium copper blue with 0.98, is that right? Well, that is going to be really purple. Maybe that's decimal error. I guess we'll find out. That was a lot of purple. Okay, well, see what we got here. So once I pull the crucible, go ahead and strike the... So just hit the bead as it pours. A little closer, you're going to hit the inner cone. The bright blue cone should be right next to it. There you go, that's it. Okay, now fire polish that place and try to get the pull into the glass. And you get that little string over there. And just hit that string so it'll melt in. Okay, go ahead and stand. And then hit a little bit more around that glass to try to melt that strain off the side. Real close. Yep, right there. That'll do it. All right. So I'm thinking that might have been a decimal error because that doesn't look like it has a full gram of manganese. That would be a ton. So that looks different than normal, though. That's kind of neat. So sort of a coppery color. So next up is B9. And so that one looks like we've got even lower amount of flux, so we expect that to be even thicker. And what else? We got high calcium carbonate. And this one has chrome and copper. So this is going to be green and blue next. All right, so composition B9. Keep on the string there, close to the top. There you go. Looks good. All right, so I definitely see the chrome green on that one. Chrome has an interesting property, and that is in glass they call it. Is it getting too hot on it? No, because if we do have a glow, do we need it? The color strikes, it's called the striking of the color. Chromium starts off being brown, and then it cools through a transition somewhere around 500 or 600 degrees where it flashes then to green. So if you look at the shard here, you can see that it's already cooled down to its green color, but that is still dark black to brown. And so it hasn't settled into the coordination. The chromium is sitting between 6 oxygens. And right now it's vibrating so wildly it's not able to hold on to all 6. Once it holds on to all 6, it turns green. If it's only holding on to like 4, it has a brown color. So the bonding environment affects the color. That's how metal coloration works. So let's zoom in even tighter for this next one. Get the full effect. All right, so this next guy, C9, so that's going to be middle, has typical glass batch, and it's a cobalt nickel. And again, hopefully that's 0.075. Because cobalt is a potent color, so we'll be able to tell right away. but we'll pour that one right there. So, all right, hit that bead on top, try to get the melt in. That is super dark. I think that might be a really high cobalt load. That might be the highest cobalt load we've ever had. You can kind of see the thin cobalt area there is usually a lot more transparent. So this is going to be like a black, almost a black in color. The crucibles you're going to hear doing what's called crazing. Hear those little tiny like sounds, like jingling. What's happening is the coefficient of thermal expansion is different from the ceramic to the glass. So the ceramic crucible is shrinking at a different rate than the glass is. As a result, it puts tension on the glass, and whenever it can't handle the tension anymore, the glass pops and forms a little hairline crack, and every time it does that, you can hear it. So it's relieving the stress of that dissimilar mismatched laminate that's on the surface of the crucible. If we were to cool it much slower, it wouldn't do that. We're kind of doing shock cooling or quenching by going from 1100 to room temperature pretty quick. So, all right, so next up we've got composition D9. That's another straight standard glass, and this is a copper iron mix. We've never tried this before, so it's mostly iron with a touch of copper. So that's going to be pulling from the left. Okay. So we're going to pour right here. Kind of work. We'll break that off for a second. Right. So 4 down. We got 7 more to go. So next up, we've got E, which is a low calcium. So remember, the sodium carbonate is the flux, you make it melt. The lower viscosity pour easier. Calcium carbonate is a flux and a cross-linker, so it kind of can go either way. So then we're adding iron manganese for this one. So iron manganese pulling from the right side. Okay. Get the string there. That's a new color. I don't think more of a orangey looking at the beginning, at least. See how close this thing can get. It's going to be really close. We'll try. So next up is F9. So it's a standard clear, 90-50-25, and then copper manganese again, but a lower, much lower loading than A. So it should be in the same genre as A, but it should be a lot less intense. Yeah, that's definitely kind of an orangey brown, that last one. So we'll pour that one right there. And pump the middle. All right. If you look carefully, you can see my gloves smoking when I pull them out. Be careful with the heat from the earlier one. You might have to kind of approach from the side. Got it? All right. I have seen people get pretty toasted on that one. Okay, so you can see that cooling down there. So next up is G9. That again is pretty straight run viscosity, and this is a chrome nickel. Low chrome, high nickel. So we'll pour that guy right here in the front. So I'm going to target right here. And that's in the left side. Nobody scorched themselves yet? All right, successful thus far. Here. You hear the chorus of Crazing now. It's crazy for Crazing. All right, so we do have some interesting new colors. I'll put some of the past years on display as well, so you can compare them. I've got more in addition to what we looked at last week. So it looks like I'm going to run out of space. So we'll probably pour the final two back on this panel. But we've got two more right here in the front. Next up is H9. Again, 90-50-25, so not too much adventure. The other class is going a little crazy. They were going with like extreme high and low on the viscosity, so that'll be different. But we're getting pretty straight run viscosity. So this is Cobalt Manganese. Again, I think that the decimal is usually to 0.01 to 0.1, and the entry is 0.27. That's almost like it could be a threefold increase over normal. So this is high cobalt. This one, we'll see what happens. But yeah, cobalt manganese. All right. So if you think about heat, you might have learned in a heat transfer class that there's 3 ways to conduct heat or transfer heat. Remember them? Conduction, convection, and radiation, right? You don't really get a good appreciation of radiant heat until holding your torch right next to that. When that thing's glowing, you start really feeling the heat. And so it adds up over time as well. But yeah, that radiant heat, it's just blasting out infrared radiation that is literally making the molecules in you vibrate, and that's how it's transferring that heat. So convection, you can see the heat rising off of it. Conduction directly to the plate, radiation to everybody. All happening as this bleeds off the energy that was given overnight to this blast by the furnace. So, all right, so zoom out for a little bit of a wider shot on this one. And we've got a few more. So next up is I9, straight run clear, cobalt, low manganese. Wow, okay. Was that a coordinated pair? Yeah. Okay. So we've got super high and super low. If we get a really bright light behind this, we might be able to see through it. I'll bring in a trouble light here in a minute, but we'll be able to see the low concentration right here next to it. So, all right, one from the middle. Much lighter. Still toasting through the glove?
No, not through the glove.
I've done that to myself before, right? The heat does go through these gloves eventually, so it's exciting. It's all right. It'll break off as soon as they're cool enough. It gets really brittle. So just trying to clear it off a bit. So I'll pour one here and one there. So we've got 2 more. So J9 is a little bit high calcium. Otherwise, well, high sodium, high calcium. So more flux on this. We would expect it to be more runny, bigger disc as a result. And then it's a copper iron. Similar to D, but higher copper and iron load.
So what would happen if we poured water on these right now?
They would shatter. I was doing a demo on that once. This actually gets hot enough that you could cook on it.
Yeah.
Like right now, I could cook on this. So I took a squirt bottle. I'm like, hey, look, it boils the water. And I was working right here on the side. Well, it's bubbling, and one little tiny droplet went up in there and hit here, and tiny little droplet. So also, we're not getting too adventurous with the glass composition. When you start changing the fluxes, you can get a high tension glass, and then they blow up after about 20 minutes. It's not like a grenade going off. It shatters radially, so it just shoots straight out and then takes an arc as it falls on the floor. But still, it makes a loud noise. You're not expecting it. And it's that energy of tension in the glass that gets relieved when it breaks. So we'll talk more about that once it cools, but using cross-polarizing lenses, you can see the tension inside glass. So we'll pour the last 2 right there. So pulling the back corner, J9. Yeah, that high flux, you can really see it spread. That one really spread out fast. So when we take diameter measurements, you'll be able to tell, wow, that's a big piece of glass by comparison.
So that should, in theory, cool quicker.
I wouldn't say it'll cool quicker. It that would be a complicated answer because as it spreads out larger, it has larger surface area of conduction to the plate. So would it cool faster? Well, yeah, I guess maybe it could cool faster. But really, it's more of the viscosity during the flow that's the main indicator. And we're going to qualitatively assess that by getting a diameter measurement. You see that most of the ones that I've called out have been the standard batch, but that one was a low flux and that one was a high flux. Can you see the difference in diameter? So we'll be able to use diameter of a nearly equivalent volume of glass at a nearly equivalent temperature as a rough indication of the viscosity during the pour. And so I'll also make copies of this so you'll have this available as you assess batches. So one more. This last one is standard viscosity glass, and it's a chrome copper. So green and light blue. So that guy's going right there. All right, composition K. Oh, chunk. Big piece of unmelted batch in there. I think what happened was there must have been a chunk and it didn't get stirred. And that one's probably going to shatter. Whenever you have inclusions like that, it doesn't bode well. So I'd say in about 10 minutes, that one's going to just go all to pieces on us. So I'll put a beaker on it so we can capture it. Let go. Well, so next up, after I'm done wrestling with this crucible, I'll show you those two videos. No, I need to cool off so it can break. That's the issue. So usually at that point, heat's the enemy. There we go.